We're going to get a lot more in-depth about limits today. And we're going to talk about limits in other contexts than just besides slope. But with that said, slope is the best application of limits. And then we'll learn after how you can actually do something that would make it so you don't even have to do limits. But it is really important you understand limits, because when we're doing derivatives and integrals and stuff like that, that this is what's going to help you understand it. Okay? Now, we're going to do limits three different ways: numerically, graphically, and algebraically. Okay? So, just to start off, there's all these different little ways to, or forms to be able to look at this at one time and understand it. Now, here is your main form. Limit as x goes to a, the limit of f of x equals L. Okay? So what that is saying, it kind of, if you go above now, as x approaches a, f of x will approach the limit. Now, for a limit to exist, it must be the same from both sides. And the ones you were doing yesterday, see, we went from the left side, we went from the right side, equal the same number. That means the limit exists, okay? Let's just add that for the limit to exist. Now, let's we're going to skip example 1 and we're going to go right to A. Okay? So, here's our first one. We're going to find limits numerically. Now, here is a really good example how you can't do it without the chart. Now, the reason being is, it says, consider the limit 1 plus x to the exponent 1 over x. Do you see that if you put 0 into here, there's no problem there, but you put the 0 into here, you will get an exponent that is undefined, right? So in this case, you can't go and just substitute this in and get the answer. So what we want to do is we want to find the limit from the left and then from the right. Okay? Now, always keep, your bearings here. This is 0. What is a really, really small number just to the left of it? Right. So negative 0.000001 kind of thing. Okay? And I just want you to understand that those, so those are the numbers closest, because some people want to put 0.999999, right? And you could see where that could be in there, right? But that's if we want to go to the left of 1, right? So the smallest number closest to 0 is negative 0.00 and positive, okay? So what we want to do, now we don't have to start too far away, but I do want to start from negative 0.1. Now, the only way to do this is to put it into your calculator. So I just want everybody to try putting 0.1 into your calculator. Yep. Okay. So what are we getting when we put 0.1 in? We'll go to 4 decimal places. Or sorry, yeah, negative 0.1. Hopefully put negative 0.1. What are we getting? Should be getting 2.86. I got 80. Yeah, The little roof. Okay, is that what you guys got? Okay, good. Now, negative 0.01. Now you got to be really careful that you don't put 0.001 into the one x and 0.01 into the other x. Okay, so you got to be really careful you're putting the right number in there. And we should get 2.7320. Okay, and if you put negative 0.001, you get 2.7196. And when you put in negative 0.0001, you get 2.7184. So the statement that I would say so far is that as x, this is approaching 0, this is approaching 2.72. Okay, now if I want to go from the right, yeah, you will find that if you went to 2, you'll never get below 2 points. Yeah, I see what you're saying. But yeah, if you keep going and going and going, it never gets below 2.72. And the 8 never gets lower. Okay? 2.72. Yeah. Yeah, like this is getting, what's that? Yeah, because we're rounding. Yeah, so if you keep going and going and going and going, this never gets below 5. Right, so we round it, right? Now again, this is such an approximation, but it's always good to see the other side to really verify. Like, I wouldn't write it down yet. You know what I'm saying? I'd do the other side and see how that's going for me. So we'll start out at 0.1. If I put that in, I get 2.5937. If I put in 0.01, I get 2.7048. If I put in 0.001, I get 2.7169. If I put in 0.0001, I get 2.7181. Yeah, so I actually don't think the 8 even goes away if you keep going and going and going. Yep. So as this is approaching 0, this is approaching 0.7 or 2.72. I think it asks to 2 decimal places, the nearest hundredth. Okay, so the way we would say this, as x approaches 0, f of x approaches 2.72 from the left. Okay, for this one, as x approaches 0, f of x approaches 2.72 from the right. Okay, and then we would say, since left-hand side equals right-hand side, the limit exists. and it equals 2.72. Okay, so that's how you find a limit numerically. Okay, we didn't do any math really, we just substituted, so that's considered numerically. Okay, now let's talk about graphically. Now remember, for a limit to exist, it must exist from approaching from the right, approaching from the left. Okay? So what is the limit at x equals -1? So x equals -1 is right there. So if we approach from this side and from this side, we will get the y value, or the f of x, of approximately, so we can just do two little things like that, approximately 3. So really, if I want to be specific, I could say, well, as we approach this from the left and from the right, we would be approaching the f(x) value of 3. Okay? Let's go across, and we'll do limit as x equals 9. Okay? So we're going to go this way and this way to 9, and we should be getting about what? Say negative, sure, or negative 4.6. It's definitely not 4.5, but you're just learning this stuff, so it'll come. Okay? What is the limit? Or what, sorry, this is, C isn't even a limit. C is just what is f of -5? Okay, so this is, it's right there, right? So it's a hollow dot. So it just equals, so there is no value. Oops, that should be equals. Yeah. There is no y value. So D is a little different. D says, let's approach it from the left, and let's approach it from the right. So if we approach it from left to right, what value would it come to? 4. So approximately 4. Okay. What about f of 2? Would equal 2, yes. It's a solid dot. No, because there is an actual value at 2. Okay? Now, the limit as x approaches 2. Now, when we go from the left, what does it approach? So as x approaches 2, y will approach 2. Yep. Yeah, because there's a way I can approach it from the right there. So from the right, as x approaches 2, y would approach -2. Okay, so since the left-hand side does not equal the right-hand side, we say the limit does not exist. Okay, so that is a graphical explanation of how to find a limit. If left-hand side equals right-hand side, that's the limit. Okay? If left-hand side doesn't equal right-hand side, we say that it does not exist, or D, N, E. Okay, now algebraically. So these will give me exact limits. So we've just done it numerically. We've shoved it into a formula as we approach it. We saw it graphically. Now we're going to actually find it by doing algebra. Now, what is the limit as x approaches 5 of -2? Now, sometimes the simplicity makes these very confusing. Because before it was kind of nice. I was shoving 5 in from the left. I was, what are you going to put it in to? Okay? Well, maybe let's draw the graph. So if I had, and this is at -2, actually, why don't I put -2 here? Because this is where it really falls on the. So, and 5 would be here. So as I approach from the left and from the right, what would be the answer? -2. So, and again, I know this isn't rocket science, but it is something you need to know because it'll come in later. But when x approaches a of a constant, it just equals the constant. Okay, so there's visually how, and there's an explanation, I think, of why it would equal that. Okay, now, let's keep going. What would happen to the limit of x as x approaches 3? Okay, so this is the graph of x, right? So here we have 3 down here. If we approach it from the left and approach it from the right, what value would we get up here? We would get 3. So this would equal 3. Okay, now if you wanted to, from the left, right, if you put in 2.5, you get 2.5. If you put in 2.99, you're going to get 2.99. Okay, if you put in 2.999, you get 2.999, right? So you can see this approaches 3. If you did it from the right, okay, so say 4, you'd get 4. If you went all the way to 3.01, you would get 3.01. If you went 3.001, you'd get 3.001. So you can see it is approaching 3. Okay, so that was the numeric way to prove it, the graphical way to prove it. So, as the limit of x approaches a of x would be x. Oh, sorry, what am I talking about? A. A is x. Okay, now here are the properties of limits, and these look way, way, way more difficult than they really are. But this one is just saying the limit as f of x plus g of x would be the same thing as the limit of f of x plus the limit of g of x. Okay? Whenever you have a constant in front of your function, you can put the constant out front and then go and just put the limit into f of x. If you have f of x, limit of f of x times g of x, that's the same thing as the limit of f of x times the limit of g of x. Division, same thing. Limit of f of x divided by limit of g of x. Okay, now this one here, you can take the exponent that is just around the function, and actually you can put it around the entire answer. Okay, now this one here, the limit of, now and this one is actually, these two are the same. I don't know if you can realize that, but that's like if the exponent was a half. Okay, so basically the square root of the function and then the square root of the, or if this was any fraction, okay, you can put it around the entire thing. Okay, now all I'm going to do is we're going to do this limit, and I mean right away I would just put in, like, what is this limit? What would this equal? Okay, this would be the limit as x goes to 1 of 1 squared plus 3 times 1, which equals 4. So that's what I would do. But this one says use your limit laws and see if you can make this thing way, way more complicated. Okay? Because let's face it, that's what math is all about. Okay? So this one here, what I could do is I could say, hey, this is the same thing. Or we'll start down here. That 8's in the way, but that's the same thing as limit as x approaches 1 of x squared plus the limit as x approaches 1 of 3x. Okay, now is there a way I can make this even more complicated? No. Yeah, I could take, so this would be the same thing as the limit as x approaches 1, x all squared. Okay, I'm using, so why don't I actually, this was law 1. Okay, and then I'm using, this is law 5. Okay, can I do anything with the second one to make it more complicated? Yeah, move the 3 out front. 3 limit x approaches 1 of x. And this was law 2. Okay, so now this would be the same thing as 1 squared plus 3 times 1, which equals 4. Yep, but it's showing you all the laws work. Okay? And maybe you could use your imagination and think, well, what kind of question could be asked they're going to make me see if I want to, if I can take it and simplify it. Okay, to find the limit of most functions, you can simply substitute the value into the function. Okay? Now, this gravy train won't last for long, but today it will, where you can just put it in and you get your answer, right? But obviously, so what this is trying to say is the limit as x approaches a of f of x would equal f of a. It's just saying most times you can just substitute it in and you get your limit, which would also be, in many cases, your slope. Okay, so let's do this example to illustrate. Now, whenever you're doing limits, you always have to rewrite limit x goes 2 until you substitute. So we're just going to go right to substitution. So I don't have to rewrite that limit statement again because I'm putting it in. Okay, so it said, well, f of x, I can put in a. Okay, now in this case, it's saying put x as -2, so -2 will replace all the x's. This equals -8 plus 7 over 4 minus 1. And this equals -1 over 3. Okay, so I just want you to make a note here because students actually do this wrong quite a bit, so let's try and be proactive. Okay, when you sub in the value, you do not write limit. I'll just put anymore. Okay, so now we're going to get into the only time finding a limit can be challenging is when we deal with 0. Okay, when you start getting 0 on the bottom, like if this one we just did, if x was approaching 1, I would not be able to just nicely solve it. Okay, so you're going to find that if it approaches your, what do we call the bad value here? Non-permissible. If this approaches your non-permissible, you can't just substitute it in and get an answer. Okay? So, if a is a constant, we're just going to talk about the properties of 0 with a. So, 0 times a equals 0. 0 over a equals 0. Okay, so those are both cool. That doesn't matter if that happens. What is bad is when you have a divided by 0. This is undefined. This is the big one that's going to take us some work. Because if it's undefined, just leave it as undefined. You can't find the limit. But if it's 0 divided by 0, this is called indeterminate. Okay, so for these, have to do some extra work. And if you look back at all the other ones that we did, they weren't a over 0, they were all 0 over 0s. And that's why we could find the limits if we did a little bit more work. So how do you do this? Well, first of all, step 1, always substitute the number into the expression. If you get a definite value, then you're done. If you get a over 0, it is undefined, so no limit exists. Okay? So this is one kind of limit. This is the second kind. But if you get 0 over 0, it is indeterminate. and this is the third type, okay? So you're only going to get 3 types. Equals a number, is undefined, or is 0 over 0. And number 3 is where that's your signifier. I got some work to do, and I can probably go find it. Okay? So the function must be changed algebraically until the limit is no longer indeterminate. So for rational expressions, you want to factor them completely and then cancel like terms. And we've already done those yesterday. And then if you have a radical, you need to rationalize or multiply by the conjugate. And I think you may be thinking, oh, I've got to get rid of stuff in the denominator. But actually, remember how we were doing multiplying by the conjugate even in the numerator? Because sometimes when you multiply by conjugate in the numerator, it can cancel with something on the bottom. Okay? And that's why we did some work with conjugates, so you weren't all confused when we started doing them. Okay, so let's just do some examples so we can have scenario 1, scenario 2, or scenario 3. Okay, so if we put in 5 here, so the first thing you always have to do is try it. So that's 5 minus 5 all over 5 plus 9. That equals 0 over 14, which equals 0. So the limit as x goes to 5 equals 0. Okay, so you're going to do this step all the time. And if it equals 0, a number, well, 0 is a number or undefined, you're done. Okay, this one here. Now see, this one's going towards the non-permissible, right? So this is going to equal 1, negative 3 plus 3, which equals 1 over 0. So this is undefined. Limit does not exist. So basically it's saying the limit is on the asymptote. Okay? Now, do you guys remember from Math 30 that what do you get on a graph when you multiply it all out and something cancels from top and bottom? Okay, so you cancel that non-permissible out. What kind of graph do you get? A line with 1 point gone, right? Now, can you find the limit from the left and the right when there's a hole? Yes, we did that on the graph, right, 15 minutes ago. So that is why asymptotes, if they turn into points of discontinuity, well, actually, they were never asymptotes. But if you cancel, it's going to be a point of discontinuity, and you can find the limit from both sides. Okay? But if you look at this graph here, 1 over x plus 3, it's just an asymptote at negative 3, so you won't be able to find the limit. Okay? So this one here, we're first going to substitute. So you will get 4 squared minus 16 over 4 minus 4. This will give you 0 over 0. Okay, so this is indeterminate. So there's no answer unless we do some algebra. Okay, so this is how you do it using the correct limit notation. So this would be the limit as x approaches 4 of, can you factor x squared minus 16? X plus 4, x minus 4, all over x minus 4. This equals the limit as x approaches 4. So you have to keep writing that every single time until I substitute. Those cancel, so that equals the limit as x plus 4. Okay? So then your limit would now, then you would just go 4 plus 4. See, I didn't have to rewrite the limit statement because I'm substituting now, and this equals 8. Now, in reality, does that y value exist? No. But as the limit approaches it from both sides, that is what it's going to equal. Now, if you ever want to test if this is true, what is a value you could just put in here to try? Sorry? No. 3.9999. If you put 3.9999 in here, you will get the answer 8. See, it says, or you could put 4.00001. Okay? But I want you to be able to still understand what's going on here. So if you to test, you can also go and put 3.9999. Actually, let's just, for sake, we'll just put squared minus 16 all over 3.999 minus 4. Okay, that's what you put in your calculator, and you do get the answer 8 as well. Because I want you to picture that graph, okay, and at this point, 4, 8, you would get this hole here, okay? Okay. Not in this case. Yeah, that's a good question, because this wasn't the slope formula. The slope would be 2, actually, I think. So. Okay, so basically I approached it from this side here with 3.999, and I got 8 as well. Okay, so I'll often do that because I'm done my test already. I just want to make sure I got it right. Hey, if it says limits approaching 4, 3.9, and you know what? Just make sure, because I've done this before. If you put an extra 9 here, then here, you get a totally wrong answer. Okay? You may think, oh, they're both really, really small, but you know what? 3.999 here and just 3 9s here gives you sometimes a very wrong answer. So I'll do this when I'm checking over my test at the end, put this in to here, and I should get the same number. If I don't, then I start questioning what I did wrong somewhere. Okay? Now this one here, okay, this one's, you're into some fun. Now, let's even see if this gives me that indeterminate, right? So that would be square root 0 plus 4 minus 2 all over 0. Okay, that'll give you 2 minus 2 over 0, which equals 0 over 0. So that's indeterminate. Okay, so how are we supposed to put in 0 into this? Yeah. See, this is an example where I got to get rid of the denominator. And right now, it doesn't look good. But if you multiply by the conjugate, so as limit x approaches 0 of root x plus 4 minus 2 over x, and I'm going to multiply by x, root x plus 4 plus 2 on the top and the bottom. So this equals the limit as x approaches 0. Okay, now when you multiply the top together, you will get root x plus 4 times root x plus 4, which is x plus 4, and negative 2 times 2 is minus 4. And on the bottom, don't go and multiply everything out, and you'll see why in a second. You only have to do it 4 or 5 times where you go, wow, I don't even know why I multiplied it all out, because I don't have to do that. Now this will next go limit as x approaches 0 of x over x times x plus 4 plus 2. Okay, now you see how these will cancel. So this would be, so I'm coming all the way down to here, the limit as x approaches 0 of 1 over x plus 4 plus 2. Now I test it. 0 will not make this undefined, so it's going to work. So that's now 1 over root 0 plus 4 plus 2. Do you see I did not have to write limit at this stage because I am substituting. Okay, and that'll give me 1 over root 4 is 2 plus 2 equals 1 over 4. If you really wanted to, you could actually just for this is determinate. Okay, it means I can determine, which would be just like example 1. If you can just put a number in, it's good to go. It's called a determinate. If you can, it's an indeterminate. Okay. So do you guys have this assignment written in your book? Okay. So page 18, 1, and then 3 to 6, the odds, and then read 1.3.